Hi! Last time we introduced our superconducting qubit of choice in QTech, the transmon. We focused on a transmon in isolation, studying its weakly and harmonic spectrum. Today, we will add the remaining ingredients that we need to perform qubit readout and 2-qubit gates. These ingredients are transmission line resonators. The resulting architecture for quantum hardware, combining qubits and resonators, goes by the name of circuit quantum electrodynamics, or circuit QED. As this name suggests, circuit QED is a solid-state version of cavity QED, an older field of physics that studies the interaction between light and matter at its most fundamental, with flying atoms and single photons trapped inside three-dimensional cavities. In circuit QED, qubits play the role of atoms, and transmission line resonators play the role of the cavities. We build these resonators from coplanar waveguide transmission lines that are terminated with either open or short circuits. For example, the resonator I show you here has a short at the far end and an open termination at the close end. Well, it's not exactly open. The resonator at this end couples capacitively to a feed line that will be used later to interrogate the scattering properties of the resonator near its fundamental frequency. The fundamental mode corresponds to the length matching approximately 1/4 of the wavelength. For this reason, we call it a quarter wave or λ/4 resonator. Resonators have higher modes of resonance as well, but most of the time we focus exclusively on the fundamental. The capacitive coupling between the qubit and the resonator is most clearly visualized by performing spectroscopy of the combined system. As this typical image shows, as we tune the qubit through resonance with the resonator, we observe the emergence of an avoided crossing. This avoided crossing is known as the vacuum-Rabi splitting. The minimum splitting is equal to twice the coupling constant G in the celebrated Jaynes-Cummings Hamiltonian describing the system quantum mechanically. Most of the time, however, we avoid this resonant regime. We tend to focus on the so-called dispersive regime, in which the detuning delta of the qubit with respect to the resonator is several times larger than G in magnitude. In this dispersive regime, there is a small but finite remnant of the avoided crossing. If we consider the effect of the avoided crossings arising between qubit resonator levels with equal total number of excitations, we learn something very useful. The ladder of photon excitations remains harmonic, but the resonance frequency depends on the state, 0 or 1, of the qubit. This dependence of the resonator frequency on qubit state is the key ingredient allowing qubit readout. We can interrogate the resonator and thereby also the qubit by measuring the transmission properties of a microwave pulse applied to the feed line with a frequency close to the bare fundamental. Niels will cover this in greater detail in his video. Moving on. When two qubits couple to a common resonator, an avoided crossing is also observed when one qubit is tuned through resonance with the other qubit. Compared to the vacuum-Rabi splitting, which you can see here, the qubit-qubit avoided crossing is smaller, by a factor G over delta. These qubit-qubit interactions, mediated by a dispersively coupled common bus resonator, are the key to doing 2-qubit gates. Adrian will discuss the specific avoided crossing that we use to implement 2-qubit conditional phase gates. Hint, it's not this one. So, let's now see examples of how transmons and resonators can be combined to build simple quantum processors. This is the first one I built back in 2008 together with collaborators at Yale. It has 2 transmon qubits and only 1 resonator. This resonator is used for both qubit-qubit coupling and readout functions. The resonator has capacitive terminations at both ends, so it's a halfway or λ/2 resonator. The optimal parameters of a resonator for readout and for coupling are often in conflict with one another. For this reason, the next generation of processors that we built in Delft uses different resonators for these functions. Here's an example 2-qubit processor from 2013. Note the common λ/2 bus resonator in the middle and the λ/4 readout resonators, one per qubit, coupled to the common feed line. Here, we see the same concept in a 4-qubit version. The planar constraints required us to have 2 feed lines. Hopefully, you can easily recognize the bus resonator, common to all 4 qubits, and the dedicated readout resonators, one for each qubit. So as a simple exercise, I challenge you to identify the bus resonators and the readout resonators in this 5-qubit processor from 2015. How many of each are there? In this more complex processor, we could get away with one feed line for all readout resonators. You will see the trick or the astuce in the next video. To motivate this next video on scalable circuit QED, note that all of these processors have a common form factor, roughly 2 millimeters by 7 millimeters, and a common location of the up to 8 ports connecting them to the external world. This reflects the use of a common printed circuit board throughout all these years. Surely a new approach must be taken to increase the qubit count. And indeed, the third generation of quantum processors completely rethinks the approach with extensibility to 100 qubits as the top priority. I can't wait to show you.